Welcome to Lesson 15B, Introduction to Particle Statistics. We're going to have a few lessons on statistics of particles. This will be the last major topic in this course. By way of introduction, here's some definitions. A sample is a collection of some measurement that you want to do statistics on. In this case, we'll always be using particles. So it's a collection of particles to be analyzed with statistics. For example, particle diameter or particle mass. Listed data is defined as a table of the sample with one row per data point. This is the kind of data you're used to in statistics. For example, you can create histograms and you can analyze things like standard deviation and stuff like that. I put together a little example using 18 data points. I arranged them in increasing order of particle diameter. A quick glance here shows us that we have 3 data points in the range 0 to 1 micron. We have 5 data points in the range of 1 to 2 microns. We have 6 in the range 2 to 3 microns. It's not real clear whether we count that 3 or not. Let's count it with this one. So there's 4 in the range 3 to 4 microns. When you tell Excel to do a histogram, it actually counts the 3 in this bin. So the histogram agrees with what we just calculated. Notice that delta dp is constant, and many statistics packages like Excel assume that you always want uniform increments in your variable. So this delta dp is always the same. Well, we don't always have listed data. In fact, we rarely have listed data in air pollution analysis of particles. So I'm going to introduce something called grouped data. This is defined as a table with one data point per bin. Bin is also called class. I'll use those two terms interchangeably. In other words, you don't have a data point for each particle, you have one for each bin. I'll use my little sample up here to illustrate. For our example with 18 points, let's make a table. Let j equal the bin number or the class number. We'll use the same ones we have up here, so there's 4 of them. We'll let dp min be the lower limit. So the first bin goes from 0 to 1 microns, so we'll call the lower limit 0. Likewise, the upper limit, dp max, is 1. And then for the other 3, we go from 1 to 2, 2 to 3, and 3 to 4. Notice that this 1 goes to there, and this 2 goes to there, this 3 goes to there. The middle value is just the average of the 2 to the left, so it's the average of 0 and 1 here, which is 0.5, the average of 1 and 2, which is 1.5, etc. It's just the middle value between this column min and this column max. Then we'll make another column, that's the bin width, delta dpj. That's just the difference between the max and the min. So 1 minus 0 is 1, 2 minus 1 is 1, etc. So these all have equal bin widths. And then finally, the number of particles in each of these bins. Statisticians like to use the word frequency for that. Well, the frequency is just the number in each bin. So that's 3, 5, 6, and 4. We just fill in these. The point is that this set of group data is typical for air pollution samples. We don't have the luxury of having a data point for each particle. Instead, we have a table more like this one, which is grouped data for the different bins or classes of particles. For example, consider a simple cascade impactor with 4 trays. Remember how we weigh the tray before, we weigh the tray after, and then we can get the mass of the particles in a certain diameter range that have landed on each of the trays. So we might have a table like this. Bin j, the dp range in microns, and then the mass in micrograms. This would be a simple PM10 impactor. Here's what the data might look like. We have only 4 bins or 4 trays. The range for the first one is less than 1. The second one is 1 to 2.5, 2.5 to 6, and 6 to 10. And then after we weigh each tray and subtract off the tare, we have the following masses in each bin. Delta dp would be the difference between max and min. This first one is less than 1, but we'll call that 0 to 1. So for the first bin, 1 minus 0 is 1. 2.5 minus 1 is 1.5. This is a pretty typical kind of sample that you get from a PM10 impactor, the simple one with just 4 bins. But the thing is, delta dp is not constant. So the standard statistics and making histograms and stuff doesn't really work for grouped data like it did for listed data. Bottom line here is we have a mass for each tray or bin or class, but we know nothing about individual particles in these bins. Another example is an optical counter. An optical counter will give you a number distribution, whereas an impactor gives you a mass distribution. Suppose we happen to have the same ranges and 4 bins in our optical counter, but now instead of mass, we have number of particles, nj. So we might have 50, 70, 122, 56. This optical counter gives us the number distribution, nj, for each bin, or the frequency, as statisticians like to call it. Our goal is come up with methods to analyze grouped data in order to perform statistics. This is pretty much what we'll do for the rest of the semester. Before I do more statistics, I wanted to illustrate that sometimes we have an optical counter and we get a number distribution, but we need to analyze a mass distribution, or vice versa. We may have a mass distribution and we want to change that to a number distribution. This is best illustrated by an example. The cascade impactors used. Tray number 5 weighs 13.2 milligrams clean and then 13.32 milligrams after we've run the sample. That particular tray collects particles between 4 and 6 microns, and we know the density of the particles. There's at SATP. Let's estimate the number of particles collected on tray 5. This is the key. We have to approximate all the particles on this tray as having the middle diameter, which is 5 microns, halfway between 4 and 6. Let me go back to my little example to illustrate. Say we're looking at this green bin here where we have 5 particles. We have no idea whether these are all around 1.1 or they're all around 1.8 or there's some distribution like this. All we know is that we have 5 particles in between 1 and 2 microns. So what do? The best we can do is say, well, let's just assume all of them are 1.5 microns halfway in between. We don't know anything different. There's no way we can tell just from this number 5 what the actual distribution is when all we have is a table of grouped data like this. So that's what we're dealing with here in this problem. So we're going to approximate that all the particles on the tray have the middle diameter as its range. In other words, we set dpj is 5 microns. Now let's do some equations. For bin J, the mass in bin J is the mass after collection minus the tare weight, or the mass before collection, this minus this, equal 0.12 milligram. That's the total mass collected in bin J. But mj is nj times density times the volume of a spherical particle. We'll use dpj of 5 microns, like I said, and then simply solve for nj. So we're estimating the number of particles in that bin as 6 mj divided by rho p pi dpj cubed. Plug in the numbers. Watching our units, I get 1.833 times 10 to the 6th. All the units cancel, but we're really talking about particles here. Particles doesn't really have a unit, but nj is the number of particles. If you want to get technical, you can say that this volume is the volume per particle, and then when you divide that out, you get particles in the numerator. Well, I asked for the answer in millions of particles, so my final answer is nj is 1.83 million particles. Now I'm going to use a particle sample from Hines in a book called Aerosol Technology. This is a grouped data set where we have 11 bins. So capital J is the total number of bins, or 11 here. This is a number distribution like you would get from an optical counter, for example. So I've labeled all these columns. We have the bin number. We have the minimum lower limit, minimum diameter in class J. The next one is the upper limit, or the maximum diameter in class J. Then I have the middle value. For this first one, it's just the average of these two. And then I have the class width delta dpj, which is defined as dp max minus dp min. 6 minus 4 is 2. And then these numbers are just the number of particles in each bin. In this particular case, if you add up all of these, we get 1,000. We call that NT, which is the total number of particles in the sample. Notice that this class width, or bin width, is not constant. 3, 2, 2, 1, 1, 4. It bounces all over the place. Typically, when you get to the larger particles, we have a bigger range. This last one is a range of 50, but there's no particles there. So all these particles were less than 50 microns. But those last 2 bins are 15 microns wide. If we plot a simple histogram of each of these bins, we get something very ugly. It's really hard to interpret what's going on here. We have some very skinny bins and we have some very fat bins. And so you expect the number of particles in a skinny bin to be small compared to the number of particles in a fat bin. But it's sort of arbitrary how we choose these bins and the ranges of these particles. This plot would change dramatically if we chose different bin ranges. So let's try to correct this. Here I added another column, which is the count per class width nj divided by delta dpj. So for example, I have nj in this first row or first bin 104 divided by the width of that bin, which is 3, and that gives me 34.6666. This one is easier, 160 divided by 2, or 80. Now I can use this column of data to generate a modified histogram. The first plot 1 was the ugly one I showed you. Now I have the same data except I'm dividing by delta dpj. So this is plot 2, and notice that it looks much nicer. It doesn't just look nice. This overall shape that we see here should be the same regardless of how we divvy up the bins, whether we have all the same bin width or lots of skinny ones and fat ones, etc. The other cool thing is we can calculate the area of one of these bins. This area is the height of the vertical axis, which is nj over delta dpj, times the distance along the dp axis, which is the delta dpj, which is just nj. So in other words, the area is just the number of particles in the bin. Well, that's nice. It gave us a nicer looking histogram. But the problem is that these values depend greatly on NT. For example, if I sampled twice as long, instead of an upper limit around 80 here, my upper limit would be around 160. Everything would be doubled. So let's do a further modification to correct for that. I added another column. This one we call F of dpj. I took my nj over delta dpj from the previous column, and I also divided by nt. For the first row, the first bin, I had 34.6667 divided by nt, which was 1,000. There's 1,000 particles total. That's where I came up with my 0347, rounding it off, of course. Why do we do this? Well, fj is now independent of nt. It doesn't matter how many particles we measure total, as long as we have enough to be statistically valid. Fj doesn't change regardless of how big nt is. We call this the fraction per class width, or bin width, fraction of particles in class J divided by class width. And I plotted that as plot 3. Comparing this to our previous plot, you can see that the shape is exactly the same, but instead of going from 0 to 90, we go from 0 to 0.09 in this case. Now, these numbers should now be independent of NT. If I double the number of particles in my sample, I should still get this same plot. Let's think about the area in this bin, which is bin number 6. This area is the probability that a particle will lie in this bin. Let's do a little math to prove that. Our vertical axis is this fj, which is nj over delta pj, and t. To get an area, we multiply by the horizontal width, which is delta dpj. And so this turns out to be nj over nt, which is the probability, or the number fraction. For example, at this bin that I highlighted, the probability is nj over nt. And if I look up here, I have 186 particles. And remember, nt was 1,000. So my probability is 0.186, or 18.6%. In other words, the probability that any of these particles that I sampled lies in bin number 6 is 18.6%. Well, statisticians like to deal with equations, not just histograms. So we can now convert this to a probability density function, a PDF. We simply take all these middle values here, dpj is the mid value, remember, and we fit a smooth curve through all those points. And in the limit, if you have an infinite number of data points, you get a smooth curve. But this is now a PDF. For a PDF, all the statistical properties of probability density functions must apply. For example, you may remember from statistics that the area under any PDF has to equal 1. Even if we have some bimodal distribution or something, the area under the whole curve has to be 1. Here that has to also be the case. In other words, the area under this curve has to be 1. Mathematically, the integral from 0 to infinity of f of dp ddp must equal 1. By the way, particles can't be of negative diameter, so we just go from 0 to infinity. Sometimes in statistics, you might have numbers that go negative, and then you'd go from negative infinity to infinity. Finally, in statistics, we always like Gaussian distributions, which are also called normal distributions. This does not look like a normal distribution. It has this real long tail on the right. So what happens if we make dpj a log scale? This now looks like a Gaussian. When that happens, we call it a log normal distribution. This also works if you plot log of dp or even the natural log of dp. You'll still get a Gaussian. Finally, I added one more column, the probability in the class. I took the column to the left of it, F, which was nj over delta dpj and nt in the denominator, and I multiplied by the bin width, which just gives me nj over nt, which is the probability. So again, for our bin 6, we had 186 particles, nj, divided by 1,000, which is nt, and I get 0.186. There's an 18.6% probability that a particle lies in bin j, which is between 10 and 14 microns. If we add up all these guys, we have to get 1. In other words, there's a 100% probability that a particle lies within all the ranges that we're measuring here, which makes sense. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.